Here's a little video review for you for your first test for Chem 110. And so as you're going back over, reviewing all of the PowerPoints, all of the lecture videos, the textbook, the homeworks, just to make sure that you are prepared, here's just a little list of items that you're going to need to know for your test. I'm not going to insult your intelligence by reading these for you. These are all of the things that we've covered in this first unit of Chem 110. I would suggest you snap a picture of this and be sure that you can check off that you are comfortable and confident with each topic listed here. All right, so of course, elements, you do need to know about elements made of our most simple form of matter, atoms, and you need to be able to look at the atomic structure and identify what it is. So what is this? Hopefully you identified this as a lithium atom. You can see its nucleus in the middle, of course discovered by Rutherford and his gold foil experiment, and then the electrons outside, discovered by Thomson. Keep in mind that all atoms with the exception of hydrogen and helium, follow the octet rule. They all want 8 electrons in their outermost energy level. And as we move forward in chemistry this semester, we're going to pretty much be looking at those electrons in that outermost energy level, the valence electrons. Keep in mind that as we're looking at the atom, it kind of has this structure, which you all are familiar with, that it has the nucleus in the middle, again, discovered by Rutherford, and then the electrons outside in that electron cloud. But that Bohr discovered that that electron cloud is divided into energy levels. Each energy level has a numbered notation. Those energy levels are then further divided into orbitals. Each orbital has a letter notation that starts with the first letter of what that orbital looks like: a sphere, a pear or peanut, a double peanut, or a flower. All right, and now how would you write the shorthand notation for this selenium atom? You will need to be able to recognize that, not so much do it, but hopefully you're thinking about this selenium atom with a mass number of 79. Of course, I can add my protons and neutrons to get that 79, and then an atomic number of 34. And so that's how we would note this selenium atom. And you'll need to be able to recognize a specific atom. And I'll always tell you what the mass is, because some atoms may have more neutrons or less neutrons than others, forming isotopes, as you know. Also, be sure you review that electron configuration. Remember, this is all about the energy. Also, remember those 3 rules that we went over that dictate where the electrons go. Hund's rule, where the electron is going to have its own orbital first. The Pauli exclusion principle that tells us that if we put an electron in an orbital, the next electron is going to spin in the opposite direction. And that, of course, the off-ball principle that each of those electrons is going to go to the lowest energy level first. So we would never start putting an electron in here first because of that off-ball principle. So what would be the electron configuration for aluminum? And you can't probably use this periodic table here because it's partly cut off, but take a second. This would be a great time to pause the video and practice. Hopefully you were thinking 1s2, 2s2, 2p6, 3s2, and 3p1. You were correct. Of course, we'd want to look at how many valence electrons aluminum has. Hopefully you're looking at that and thinking 3. Those are the 3 in the outermost energy level, which is the 3rd energy level, both S and P. Another way to write this electron configuration for aluminum would be the Nobel gas configuration that's shown right there. And I know you've been practicing on that. How about Se, the electron configuration for selenium? Hopefully you said 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p4. How about valence electrons for selenium? Now, for this atom, I personally would draw this atom out because I can see that it has 4 energy levels. The highest energy level, of course, is the 4th one. And so in that 4th energy level, selenium has 6 electrons divided between the s and p orbital. And a shorthand way to write that. Taking a look at this aluminum atom. So that's just what that atom looks like. And then let's take a look at this atom. What is this? The protons are red. I see it has 3 protons, positive protons in the nucleus, but I see it only has 2 electrons out in its first energy level. And so obviously this is not a neutral atom. So what is it when it's not a neutral atom? Hopefully you're thinking, that's an ion, and it's got to be a lithium ion. And I could write it like this. This atom has a mass of 6 because of the contents of the nucleus and a +1 charge. Now keep in mind, oftentimes, if you're reading in a book, you're going to find just a plus sign as opposed to that +1. It means the exact same thing. How about this? If you need to pause the video for a moment to count, feel free to do that. And hopefully you're thinking that was a fluorine atom. And we can write that fluorine atom like this. Now, of course, there are fluorine's valence electrons. And the other electrons are called core electrons. They're not the valence electrons. Let's take a look at this next one. Again, a great time to pause the video. Hopefully you were thinking, this is a fluorine ion. This has gained an electron. And so just like for the positive ion, this negative anion, we sometimes just put a minus sign there, just like that. Of course, here's a neon atom. I'm sorry, I should have told you to pause the video. You also need to know the location of the various elements on the periodic table, like the noble gases. Don't forget the noble gases are, right here. I should have circled it for you. In this, I like to call this group 8 as opposed to 18. In this group 8 right here, with the exception of helium, they have 8 valence electrons. Of course, helium only has 2 because it only has electrons in that first energy level. And all the other atoms, of course, want to be like those noble gases. They want to have that full valence shell. All right. We also worked on measuring in this unit. Can you identify the base metric units for volume, mass, and length? If you need a second to pause the video, feel free to do that. Hopefully you were thinking volume is liters, mass is grams, and length is meters. Also, looking at the periodic table, you need to know the location of the metals. Hopefully you're thinking, yes, the metals are over there on the left side. They like to give away electrons to become positive ions. That's why metals are such great conductors of both heat and electricity, because they don't hold on to their electrons tightly. How about the nonmetals? Yes, on the right-hand side. These atoms tend to have a lot of valence electrons. Typically, they're smaller than the metals on the other side. And they typically have a high ionization energy, which means it's going to take a lot of energy to remove an electron from a non-metal. They also tend to gain electrons and form negative ions we call anions. How about the transition metals? Hopefully you're thinking, that's still got to be on the left. That's the metal side. Yes. Transition metals right in the middle there. These are the B group elements right here that you should know. Now, as we're taking a look at matter, we know that matter mostly in our world exists as mixtures, both homogeneous and heterogeneous. If we have a pure substance, remember that's either a compound or an element, and any of these can exist as solids, liquids, and gases. You will need to be able to recognize them and their characteristics, their volume, pressure, and their relative amount of kinetic energy. All right, take a moment and see if you can solve this problem right here. Great time to pause the video. Hopefully you figured out that you divided the mass by the volume and you came up with 0.0833. And of course, you've got to round that to two significant figures. You're also asked to put this number in scientific notation. So moving that decimal over 2 places, because 0.083 is a very small number, you have a negative exponent here. Of course, and this is an often confused topic when we're dealing with volume. The metric base unit for volume, we've only in the lab been measuring in milliliters, but the actual base unit for volume is liters. And I'm hoping that's coming up. Yes, there we go, liters. All right, take a look at our fruit salad. How would you classify this mixture? Hopefully you're thinking it's heterogeneous. All right. Take a moment and pause the video, see if you can answer this question. So as we're adding each of these pounds of different seafood up, lining up the decimal there, remember the rules when you're adding and subtracting. We're going to have to take a look at our measurements and notice my shrimp is only to the 10th place. So that's where I'm going to have to round this answer to that 10th place. And so when I do that, I'm going to have purchased 8.5 pounds of seafood, not 8.47. How would you classify these two? Now, of course, we're looking at the particles here. Tap water is going to be a mixture, but it is going to the naked eye, it's going to look homogeneous. Whereas our distilled water is a pure substance. It is a compound. And don't forget the octet rule. As we move into Unit 2, we'll be talking about more ways to show those valence electrons. All right. How about if you have this oxygen atom? What's its mass number? If it has 10 neutrons. So hopefully you're thinking, well, that must be a mass number of 18 because oxygen always has 8 protons, plus the neutrons would be 18. All right. Can you locate metals, nonmetals, and semimetals or metalloids on the periodic table? Hopefully you are thinking just like this. Their locations. I should go back here and just point out hydrogen really quickly. It is on the metal side. It's in that first group, those alkali metals, because it only has 1 valence electron. But of course, hydrogen is a nonmetal. Make sure that you're familiar with all the metric units and prefixes. Also, you'll need to know about the periodic trend. So going left to right within a period, so like across the period, atomic size does what? Hopefully you were thinking decreases. And it's decreasing because as we're going across this period, the electrons, they're still all in that same energy level, and they're getting pulled into the nucleus more tightly, making the atom smaller. You'll also be given multiple measurements, and you'll have to figure out which is largest and which is smallest. So, how do you attack a problem like this? Well, I see I've got pounds, kilograms, and grams. So I'm going to select the unit that I feel most comfortable with. And I'm going to convert all the measurements to that unit. So I'm going to take my pounds and convert to kilograms. I've got my kilograms already in kilograms, and then I'm going to convert my grams to kilograms. And I'm going to see that the largest is the 0.84 kilograms that I started with, and the smallest is the pounds. Okay, you might be given a variety of electron configurations and asked some questions, like which one of these atoms has 4 valence electrons? And a couple of my superscripts I see did not turn out right. And so hopefully you're looking at that, which represents a transition metal. Remember, transition metals are filling their d orbital. And so I noticed that I only see 1 d orbital here. And which one is a group 1 alkali metal? So that right there tells me 1 electron in its valence shell. And so that would tell me that right there. So make sure you're practicing things like that. I'll give you a second to look at these answers if you need to. So let's look at valence electrons. Which atom is not? That's one of those kinds of questions that you will see on that first test, not correctly matched with its number of valence electrons. Hopefully you figured bromine. Calcium is one that people often look to, but don't forget that calcium is filling its d orbital, and the d orbital is 1 behind. All right, can you convert decograms to nanograms? And put that answer in scientific notation. So this is the entire scheme of all of the metric prefixes in order with the base unit, meters, liters, grams in the middle. All right. And so I'm starting at my decograms and going down to my nanograms, moving that decimal as I go. And so forth like that. So make sure that you have practiced up on those. All right. How about if you had the numbers, could you match those to the prefixes? Hopefully you were thinking kilo, centi, milli, and nano, or 10 to the minus 9. All right. Here we go. We've got some students doing some measurements. What's the difference between accuracy and precision? They're supposed to be measuring exactly 10.0 milliliters. And because it's exactly 10.0, or 10, we call it 10.0 to bring it to 3 significant figures. And, oh dear, let's take a look. It looks to me as though more precision is B, and I apologize, my circle is not in the right spot there. It looks to me as though person A is more accurate. Of course, I could determine precision by doing my standard deviation and accuracy by doing my percent relative error. All right, can you do this conversion? Great time to pause the video here. Hopefully, as you were converting joules to kilocalories, we first have to convert joules to calories, and then calories to kilocalories, because kilocalories has that prefix kilo. It's just 1,000, so we've got our calories, and now we'll simply convert that to kcals, or kilocalories, and round to 3 significant figures. And of course, we can put that in scientific notation as well. Still knowing about those periodic trends, going from top to bottom down a group. So that would be like hydrogen, lithium, sodium. Does atomic size increase or decrease, and why? Hopefully you were thinking it increases. And the reason is because every time as we go down, we add another energy level on the periodic table. Every period going across corresponds to an energy level. How many neutrons would this particular atom of chlorine have? Hopefully you were thinking 20. And can you calculate the average atomic mass? Take a moment, pause the video, and practice that one. Hopefully you worked it out the same as me and came up with something around 24.3. Again, when we're doing this average atomic mass, we're not so concerned with significant figures. All right, got a quick quiz for you. All right, electrons in the outermost energy level are called ionization. Hopefully you thought incorrect. False. Those electrons are our valence electrons. When atoms emit light, this happens because electrons absorb energy, become excited, and jump to a higher energy level, then settle back down. Hopefully you were thinking true. Yes. An isotope has the same number of neutrons and protons, but a different number of electrons. Hopefully you're thinking false for that one. The off-ball principle says that electrons enter the lowest energy level first. Hopefully you were thinking true. I think my false was supposed to disappear there. The size of an atom from the center, the nucleus, to the outer edge, those valence electrons, is the atomic radius. Hopefully you were thinking true, that is true. All right, so this week, just one last little thing to do, study for that test. Make sure you've submitted experiment 4 and activity 2, and then we'll get started right away on unit 2.